Hey guys, this is Ed with the Kaizen effect. Today, what I intend to do is continue our discussion of Lagrangian mechanics, which I started in our previous video, and establish a robust understanding of calculus of variations. Now, in that previous video, what we did was I showed you how Lagrangian mechanics is sort of like a reformulation of Newtonian mechanics, which strives to do the following. It asserts that there are many paths that particles or systems of particles, systems of objects can take or evolve into, okay? And what Lagrange did was he said, okay, I want to use my mathematical prowess to define them instead of using these convoluted free body diagrams and vectors that are used in Newtonian mechanics. So how did he do that? What he did was he said, okay, there's these ton of different paths the particles can take. I'm going to restrict all the potential paths they can take to those paths which conform to the laws we know of the universe. So these are the laws of conservation of energy, conservation of mass, conservation of momentum, and, Newton's laws of motion. Now, in order to do this, I also noted that he applied the principle of least action, which is sometimes referred to as Hamilton's principle. And this basically asserts that the particles, the way in which they move, the paths they take in order to conform to those laws are paths which minimize the action, right? It allows them to take the path of least action. And in order to do this, when you hear the word minimization, that's a trigger word for calculus, right? So you need to minimize this function, this action function. But in the previous video, what we found is that we can't use the nice framework we established in Calc 101, right? We can't just take the derivative, set it equal to 0, and find the points of the function that satisfy that. Because the action, that's basically something which is defined by a functional, okay? So a functional is like a function of another function, right? It's this S guy here. We see that the action is an integral which, it's a function of other functions. So in order to minimize that, in the previous video I put out, we worked to get to this result known as the Euler-Lagrange Equation, okay? Basically what that does is it says if we want to minimize a functional, which we're going to need to do in Lagrangian mechanics, what you need to do is you need to take all the paths that a particle can take or that a system of objects can evolve into and restrict those paths down to the paths that satisfy this equation here. So this is known as the Euler-Lagrange equation, and when you, restrict those paths down to those that satisfy this, you minimize your functional, and that gets us to the result that we want to get to. Now, I tend to say that physics is the philosophy of life translated into the language of mathematics. So in order to understand physics as fully as possible, we need to know the language of physics. And the language of Lagrangian mechanics is calculus of variations, and in particular, using this equation here. So in this video, what I want to do is I want to expand upon the previous video I put out, which you should definitely watch right here. If you haven't watched it, I highly urge you to watch that, because you want to understand where this comes from, how it can be used, and how you can apply it such that when we're applying it in Lagrangian mechanics, you have this nice framework that you can refer to and you feel comfortable with everything. So that's what I'm going to do in this video. I'm going to work through an additional example that helps you understand what's going on here, helps you understand how you apply this, and what it can do for you, how you can use it outside of physics too. So that's what we're going to do in this video. Okay, so in order to really do that, the example problem we're going to work on is a classic problem in calculus of variations. This is the problem known as geodesics. How to find geodesics in geometry. What does that mean? So basically a geodesic is like the smallest or the shortest path on any kind of geometry. Now in the previous video, I showed you how to prove that the shortest path between 2 points on a plane is a straight line, and that makes sense, and that's intuitive. And furthermore, that helped us show that when we applied this, we can get a result that jives well with our intuition, right? Because we would expect the shortest path between 2 points to be a straight line. Now, what happens if we want to do that with something that's not as intuitive? If we want to take any kind of geometry and find the shortest path between 2 points, how do we do that? How do we solve that kind of problem? Well, we're going to do that right now in this video by applying the Euler-Lagrange equation to a function L to find the shortest path for any surface that we encounter in nature. All right, so how exactly do we do that? I'm going to show that by applying the same ideas to a cylinder. We're going to do that for the geometry of a cylinder, and I'm going to generalize that such that you can do it for any kind of geometry you encounter in nature. Okay, so how do we do that? The first thing we need to do is we need to derive a function for the distance on any kind of surface, okay? Any surface, you name it, whatever it is, okay? Because what we want to do is we want to minimize that distance, okay, between the 2 points. So we need a function to represent that. So given any kind of geometry, regardless of whether it's a cylinder or what have you, if you have 2 points, let's say a point here, we'll call that P1, and another point here, we'll call that P2. If you want to find the shortest distance between these 2 points, which might look something like that, it could look like that, it could look like that. We don't know yet. We're just guessing here. What you need to do is, again, you need to figure out how to calculate that distance. So in any kind of geometry, what you want to do is you want to take a look at an infinitesimal segment of that line connecting the 2 points. So we take this infinitesimal length, we blow it up like so, and we get the following. So we're going to have this line, which is infinitesimally small, we're going to call ds, okay? So in order to figure out ds, we're going to have to figure out these 2 distances here. One way to do this is we can use the Pythagorean theorem in 3 dimensions. We know that is ds squared equals dx squared plus dy squared plus dz squared. And again, these differentials are infinitesimal lengths, okay? So we could use this general equation to derive everything, okay? What we need to do that is we need to represent these variables in the kind of coordinate system that we're using. Here we have a cylinder. So we will use polar coordinates to express that because that's the easiest way to work with this system, right? It's the easiest way to work with this geometry. So what you would do is, first you would define x, y, and z in terms of your coordinates. Here we're going to have a constant radius r, and we'll call this r, and I guess I'll put an axis here. That'll be x, y. This is going to be z. And what we see is x can be defined by, I'm going to have to put in something else. So this is going to be theta, and that's going to be from the x-axis. Actually, before I proceed, it's better to write the axis like this, because usually we want to use the right-hand rule. So we want x, when we cross x into y, we want to get z, right? So this allows us to get that. So we're going to define theta as the angle from x going towards y. And you can see that right up here too. So the next thing we're going to do is we're going to define x. How do we define x? Well, if we blow this up a bit, if we take the top here, we know that in the center we can have this radius r. We have this guy here. This is going to be x. This is going to be y. So what we could do is we can see r. We can use trigonometry, right? If we want to get to this point, we can use r cosine theta. So again, what we're trying to do, we're trying to find points on this surface, this geometry, the surface of the cylinder, because our points are going to be on that surface. We're trying to find the shortest distance between any kind of point on that surface. So to get to that, r is always constant. to make that, I guess, more self-explanatory, we can label this, or I guess this will be our coordinate. We can label this as big R. So x becomes R cosine theta, okay? The next thing we want to do is figure out something for y. Using this diagram here, we can see if we take the sine of this guy, we're going to get the vertical dimension. So we could just take r sine theta, and we get that. If you're not comfortable with your trigonometry, if you haven't looked at that for a while, one way to think about this is, sine is opposite over the hypotenuse, right? So if it's opposite over the hypotenuse and r is the hypotenuse, you see r times opposite over hypotenuse, they're going to cancel, and you're going to get basically this distance here. Same thing applies with x, right? The cosine is the adjacent over the hypotenuse, right? So if you have r, which is the hypotenuse, times adjacent over hypotenuse, you end up with the adjacent dimension, which is this guy right here, okay? So the only remaining ingredient here is just z, and we're going to define it as such. So the next thing we want to do is get the differentials. So in this case, this is pretty easy because r is constant, theta is going to be our independent variable, and so we could just differentiate these guys. So dx becomes negative r sine theta d theta from the chain rule, right? So I just took the derivative of cosine, that's negative sine, and then I took the derivative of the variable inside. We do the same thing for dy. Derivative of sine is cosine, so we get r cosine theta, and then chain rule again, d theta. We can do the same thing with z. This guy's easy. dz equals dz, okay? So if we have dx squared plus dy squared, or rather, I'm going to erase this guy. No, I guess I'll leave it there. Let's bring this guy down here. So we get ds squared is equal to, we plug in all this stuff, we get r squared cosine squared theta plus r squared sine squared theta plus dz squared. All right? So what we want to do next is we can group the r squared terms. We can say this is equal to r squared cosine squared theta plus sine squared plus dz squared. Now this guy is 1. That's a trigonometric identity, right? So this gives us ds equal to r squared plus dz squared. Or rather, I'm missing the d theta. So this guy should have d theta squared. This should have d theta squared in here. So it actually becomes r d theta squared. All right, so that is the distance we can use. And I'm going to circle that in red. Now, a good thing to do with any kind of derivation you do in math or physics is if you do something once, you should be able to replicate it with a different alternate route. So to better understand what's going on here, I'm going to do that. You can use this method by defining the coordinates, taking the derivatives, defining the differentials in essence, plugging them into the Pythagorean theorem, and that will get you a result for ds regardless of your coordinate system. That will always work, and it will always work for any kind of surface. But what if we're working with the cylinder here? How can we do that in a much easier way? I'm going to show you how to do that right now. All right? So you can do that geometrically. You can do that from your geometric understanding of the problem that you have here. So if we take this guy here, we can think of this as like if we took a sheet of this guy off that had these points and laid it flat on this board, we would probably see a straight line between them, right? That would make sense, right? And furthermore, we would think that the distance between here is just a change in z, right? Can you see that? Because this is the direction of z. So if we unravel that, the distance up has to be dz. So that makes sense. But the question is, what is that going to be? What could that possibly be? We know that's going to be basically this distance here. It's going to be like if we had the cylinder like this, it's going to be the distance along that surface, the curved distance, okay? So how do we figure that out? Well, what we could do is, if we took basically a slice, if we took a knife and chop this guy up, let's think it's maybe a cylinder, it's a piece of sausage or a pepperoni, we just chop that and look straight at the top, or like an element along here, so an element that contains this ds, what we would find is it would look something like this. We would get something like this. We'd have, again, that constant r. And then we would have theta defined like this. Now, to get to the 2 points on here, on this infinitesimal length, how can you find that? Well, we know that r has to remain constant because it's always on that surface. And we know that to get to this point on the surface, you might have to go like that, right? We have to move along the surface here. So that's going to be a change in theta, right? It's going to be a change in this guy, right? That theta right there. So we're going to have a change in theta. I'm going to call that d theta. Now, the key to understanding this is we can use trigonometry again, and we can fit a triangle onto this diagram here. But the important thing to notice here is that theta is infinitesimally small. It's infinitesimally small. So you would expect this distance of this triangle to be very small too. Now, if you have these vertices, these 2 points along the surface, what you're going to find is that basically if this gets smaller and smaller and smaller, which corresponds to a small angle, this distance, the distance basically between this line of the triangle and the surface of the cylinder, this guy, is going to get smaller and smaller and smaller and smaller until the distance along that curve is the same as the straight distance in the triangle, okay? So if we could figure out this distance, that's going to correspond to the distance, the curved distance, okay? So what you can do is, we know that from trigonometry. We have d theta here, right? We have d theta. So if we take our sine theta, basically that angle, this guy is going to become r sine, I'm going to put d theta in, okay, to represent a small angle, okay? So you might be thinking, okay, that doesn't look like r d theta. How do I get this down to r d theta? And I'm going to show you it's actually an approximation. What you can do is the following. So you can take sine theta and you can take advantage of 2 things. 1, the Taylor series polynomial, and 2, the fact that d theta is small. And it's very important to understand this because this is an underlying theme in a lot of physics derivations, even solving problems in physics, and also in mathematics. So I'm going to run through this. I think it's a valuable exercise. And what you need to do is, first, we need to figure out what that Taylor series is. I'm going to take the result because I'm assuming you guys have gone through calc to Calc 2, which you derive Taylor series and know how to do that. So the result for sine, I'm going to put theta here, is the following. It's the sum from n equal to 0 to infinity of -1 to the n over 2n plus 1 factorial times theta to the 2n plus 1. And furthermore, when we simplify this or take the first few terms, it becomes theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus so on and so forth, basically the other terms, okay? So what can we do about this? We know that the theta we're using is very small. So here's the argument I'm going to make here. I'm going to say that all these terms after the first term are negligible. Why? Why are they negligible? It's super important to understand this. So I'm going to walk through the logic for you because I found that sometimes a lot of lecturers do not do that. I want you to understand this. So if we have a very small value, d theta, and we square that, what do you get back? You get a much, much smaller value, right? For example, if you take 0.2, 2/10, and square that, you get 4/100. So if you had 0.2 and square it, so I'm going to do that, like x squared is the function here, what you end up with is 0.04. So that's much smaller. What if it's even smaller? If you have something like 0.02 and you square that, so that's 2 over 100, basically you get 4 over 10,000ths, right? That's much, much smaller. That's much, much smaller. So that's basically 0.0004. Yeah, that's what it is. So you can see, like, it's much smaller. So as this gets smaller and smaller and smaller, when you square that term, it gets even smaller, okay? Do you see the trend here? So if this is infinitesimally small, then if we square it, it's basically negligible. It won't affect this number, right? Because if we have like 1 and we subtract 0.0000001, what do you get? It's like 0.9999999. Not much of a difference. You essentially have 1, okay? And based upon your level of accuracy, you can ignore those terms. So if we're cubing a really, really small number, what happens here? What happens? It means that these guys are approximately 0 in comparison to this guy. So what we can say is sine theta is approximately equal to theta if theta is much less than 1, okay? We have this case because d theta is infinitesimally small, so sine d theta becomes d theta, and this guy holds true. So what we can say is this distance is going to be r d theta, and what we see is that when we take the Pythagorean theorem here, you know, ds squared is equal to this guy squared plus dz squared. What happens? Bam! We get the same result, okay? So you can do that either way. You can use your geometry sense, or you can use the method I used previously, which is trusting your mathematics. The important thing to note is that these guys are both equivalent, okay? So, you know, that increases our confidence and allows us to go ahead with this result. All right, now that you have an expression for an infinitesimal length along any kind of surface of interest, what do? In our case, this expression ds is going to be an infinitesimal length along the cylinder. What you do next is you want to add up all those infinitesimal lengths. And when you hear the word add up infinitesimal quantities, what should that trigger? That should raise a red flag for calculus, for taking an integral. Okay, so we're going to have to integrate. We're going to have to add up all these little intervals until we get the total distance between point 1 to point 2. All right? So before we do that, we need to take out one of these differentials. What we're going to say is that z is a function of theta here, because as we rotate along this cylinder, z is going to go up or down depending upon where this point is. So what we can do is we can pull this d theta squared out by taking the square root of, we're going to take d theta squared times r squared plus dz d theta, so the derivative squared. And we see we didn't change anything here because if we multiply this through again, we get r squared d theta squared plus the d theta squareds, and the d theta squareds cancel, plus that dz squared. Okay, that dz squared comes back. So we didn't do anything here. So next what we want to do is we want to pull out this d theta. So we're going to end up with r squared plus dz d theta. This guy's going to be squared. We take the square root. Our d theta is out. Now again, so we're going to move along this theta direction and add up these guys. Add up these infinitesimal lengths along theta. So again, that triggers the integral. So we're going to integrate between theta 1, which is going to be basically right here, and we're going to go to theta 2, which is basically right here at the second point, and add up all these infinitesimal lengths. That's going to give us the exact distance between these 2 points. Okay, so that's great. This guy right here is our functional. Okay, this is the functional because we see the distance between these 2 points is a function of another function. Furthermore, we have these integrals in here. So in order to minimize this and find the path z sub theta that shows us the minimal path between these 2 points, what we need to do is we can't use our nice tools in Calc 101. We can't take the derivative of s with respect to some variable, right? That doesn't even make any sense here. What we need to do, as I showed in my previous video, we have to employ the Euler-Lagrange equation right here. So what we're going to say is there's an infinite number of paths that can connect point 1 to point 2, right? Could be this, could be something like that, could be something like that. There's an infinite number. However, to find the exact solution to our problem, to find the path that minimizes this functional, or rather the shortest path, what we need to do is we're going to say the space of all solutions has to be restricted to the subspace of solutions that satisfy this equation here, because we showed in my previous video again that this minimizes this function. Okay, so how do we translate this over to this function now? We need to look at the equation and see that this guy here, this is f. And furthermore, it's f z sub theta, z prime sub theta, and theta. Okay? So the function now is always going to be an integral of this function f. And that function f is always going to be a function of the functions that define the path that we're trying to find here. Okay? In this case, we're going to say z is a function of theta. In the previous video, when we were finding the shortest path between 2 points on a plane, what we did was we defined the distance between them, the path, as y sub x. Okay? So same thing. We're just changing variables to conform to our problem here. So y is like our z, right? That y is the path we're going to take. And furthermore, x, that's the independent variable. Okay? So in order to minimize this, we're going to have to employ this, and we're going to have to take the derivatives of this function f. So let's do that now, okay? These partial derivatives. So df dz, again, z is the same as y here. Df dz is going to be 0 here, right? We don't have z in here. We don't have z in the f. That's nice. Next, we're going to find df dz prime. That's this guy. Okay? So this is a bit harder. We have basically this to the 1/2. So we can multiply that 1/2 in the front. So we get 1/2 times everything inside, which is r squared, plus, that's not partial, dz d theta squared to the negative 1/2. So basically it's 1/2 minus 1, that gives us the negative 1/2. Then we got to use the chain rule, right? Because this is with respect to z prime, dz d theta. So we want to integrate next everything inside this, basically everything inside here. So we see we have z prime squared, so that becomes 2 z prime. Okay, so the 2's are going to cancel here, and we end up with z prime over r squared plus dz d theta squared. Okay? All right, so we got all the ingredients for this. Now we need to plug them into the Euler-Lagrange equation, okay? So again, this is not rocket science. This is not hard. We're just following a formula here. But it's important to understand what this means, right? It's important to understand the y variable, the y prime variable, the x variable. Because if you don't understand that, you don't understand the language, and hence you can't understand what this is trying to do. You can't understand the mechanism at play here. So make sure you understand this. Make sure you understand how it's derived. Because if you understand how it's derived, you understand what these variables mean. And if you don't, watch my previous video in which I derive that. I do a really great job of explaining it. If you have not watched that, again, check it out right here. I would recommend not even going any further until you watch this video. And once you understand that, it's going to be easier to apply this because you understand the language. Again, physics is the philosophy of life translated into the language of mathematics. To understand physics, you need to understand the mathematics. Okay? So let's proceed with the problem here. So what we want to do is, I guess I'll continue on the side here. We're going to plug these guys in to this guy here. So df dz, I guess I'll write it out. So df dz, basically the function of the path we're considering, minus d theta, which is the independent variable used to define path, df dz prime equals 0. We see here, yeah, that's fine. I saw that as df dz. Disregard that. What we see here is that df dz is 0. This guy becomes 0. So we end up with d theta of this guy, of z prime, over, actually, yeah, I missed a square root right there, right? Yes, because that negative 1/2. So r squared plus, I'm going to write z prime in here. Z prime is dz d theta. Just trying to simplify the board mechanics here. So we got that square root, that is equal to 0. Now, an important lesson here. If you're dealing with calculus of variations or Lagrangian mechanics, because it's going to be using the same Euler-Lagrange equation, if you end up with this guy, what you can say is that you can go right away and say that this guy is equal to a constant c, okay? Why is that? Because we see here, when that guy's 0, this guy has to equal 0. And when the derivative of something equals 0, whatever is inside has to be a constant. This has to be a constant, right? To be 0. This has to be a constant, okay? So we know everything in here is a constant. And if you're encountering this situation in a future problem, you can use this simplification. That's pretty nice, right? So you can always use that. So let's continue with the problem here. I'm going to get some more board space here. What you want to do next is, again, we can take advantage of that fact I just proved. We say z prime over r squared plus z prime squared is equal to a constant c. All right, so how do we proceed from here? Well, you have to ask yourself what you're trying to do with this problem, right? We're trying to find the path between these 2 points that minimizes the distance of that path, okay? So we're trying to find that path, z sub theta. We're trying to solve for z here, so we got to isolate z somehow. What we could do is we can square both sides. We end up with z prime squared over r squared plus z prime squared. That's great. We have 2 z prime squares, so maybe we can isolate them. But before we do that, we can note that c squared is a constant, right? C squared, you know, if you take a constant 2, square that, you get 4, right? So this is another constant, a. I'm going to use a. You can use whatever you want, okay? So how can we proceed with this? We can take this bottom here, multiply it over here, and end up with z prime squared is equal to a times r squared plus z prime squared. Okay, we're making some headway. Now we want to isolate the z prime here. So we can say z prime squared times 1 minus a. So I'm taking this az squared, pulling it over here, and that is equal to ar squared. Okay, we're almost here. We're almost done. We're going to take z prime squared. We're going to divide by this guy, end up with ar squared over 1 minus a. All right? And the final thing we can do is take the square root. So when we do that, we find that that was a constant. We squared it. So a is a constant. We know r is a constant because r is fixed to the outside of our cylinder. We also know that 1 minus a is a constant. So a, which is a constant, times r squared, which is a constant, is another constant, divided by this constant here. What does that give you? That gives you a constant, right? So all this stuff, I'm going to call that m. And we see that if we integrate this z prime, this is dz d theta, what we end up with is z sub theta is equal to m, a constant which I cleverly named, plus another constant which I'm going to cleverly also name b, and we end up with the following. Well, that's an interesting result. This shows us that the shortest path between any 2 points on a cylinder is again a straight line, but it's not a straight line like the previous one we saw. It's a line that is going around the cylinder, right? It's defined by this theta. So the way in which you should think about this, what this really means is that if I draw the cylinder, a new cylinder, if you have 2 points, let's say this guy right here and that guy there, the distance is a straight line if we like pulled off this sheet around the cylinder, light it flat on this paper. So that corresponds to a helix, something like that. It's going to be a helix, but it's going to be curved. It's going to be more curved than the previous example we showed in my previous video. I guess a better way of thinking about this, a helix is, something that it's sort of hard to do it on a 2D geometry, but it's like a spring in essence. So the shortest path between any 2 points on a cylinder is the path that conforms to a specific helix or a specific spring. That's what we got here. So we were able to prove that. That seems to make sense, and we can take this process and we can apply it to any kind of geometry we encounter. Another classic problem that I can work through if you guys are interested, leave a comment below if you are, is the geodesics of a sphere. And you can go through the same kind of procedure here and figure out that the shortest path between 2 points on a sphere is basically a geodesic on the sphere. Basically sort of like a line of, I'm not sure if it's latitude or longitude, but it's basically a line that goes straight down to the point. So we learned that we can apply this process here to figure out the shortest distance along any kind of geometry, which is very nice, especially if you're doing some kind of physics that's contingent upon the length of something, and you can use that there. You can also apply this also to, I guess, a functional that has 2 integrals. So maybe if you're trying to minimize the area along something. The example I would use is maybe you have a heat flux flowing through an area and you want to minimize the total heat transfer through that area. If the heat flux is constant along a segment of area, what you can do is, you can minimize that area such that the heat transfer is as low as possible. So you get a functional with dA, and you would get that dA. Basically, I guess, let me talk less abstractly here. So you would get maybe S is equal to some function f dA. That's going to be, or rather, I guess I could put a Q here. This would be for the heat transfer. And you could apply this to F here. So it would be a little more complicated, but we're basically applying the same thing here. Same idea. So we found in this video that in order to minimize any kind of function now, we can apply the Euler-Lagrange function, and it's important to realize that the y's here, these are the variables that define the path, right? It's the function for the path. And the x is the independent variable that is used in the function for the path. Okay, so it's important to realize that kind of stuff. Make sure you feel comfortable with this. This entire video is intended to help you to establish that comfort. But again, I feel like a broken record here, but physics is the language of, physics is like the philosophy of life. And it's like the philosophy of life translated into the language of mathematics. In order to do Lagrangian mechanics, we're going to have to understand the language of it. That's the language of calculus of variations, and we're going to be using the Euler-Lagrange equation very prominently throughout the course. So I might run through a few more examples to help you get more comfortable with this stuff. But you want to make sure you understand this. If you do not, check out my video in which I derive it right here. Make sure you understand that. Make sure you know what I'm doing so that you can understand this, such that you understand the power behind this tool, what it's capable of, and how you can apply it in a way that doesn't allow you to mess up your physics and your mathematics. And once you do that, you'll be well on your way for understanding Lagrangian mechanics. Thanks for watching.